Welcome! This tutorial will showcase how to prepare toolpaths for milling a casting formwork in XPS. Before going into Fusion 360, this specific tutorial will also show how one may prepare the actual casting formwork 3D model. So let's open our Rhino model here. And here we have the positive of the model that we want to achieve after casting. So the first thing we'll do is to create a box representative of the XPS sheet that we are going to use. So we'll start at the origin, and then not including the flanges in the dimensions, but as a parenthesis one can say already at this stage that we don't need to actually physically remove the flanges, as long as we don't include them in our representation here, since that would possibly lead to leaks. So we'll only add the length of 1155 without the flanges, and the width of 555 without the flanges, and then the thickness here will be 100 millimeters. And then we'll make sure to select everything, Ctrl A, except control clicking the XPS sheet. And then we can actually already at this stage, we can move with M, this from the midpoint, and then we can lock the axis of movement with Tab, and then we can go safely to the mid of the sheet. And this yields us a very generous margin of 67.5 millimeters to the edge of the XPS sheet, not including the flange. And for casting with plaster, it is recommended to have a margin of at least 25 millimeters or so, laterally. In the bottom, we may leave at least 12 millimeters. Having made sure that all of the model is selected here, we can rotate the model, flipping it upside down, rotating it along the long x-axis. So we'll do 180 degrees. Now we can move with M and then constrain the movement to the vertical z-axis only with V. And then we can select the top here, which was previously the bottom, and make sure that this is co-aligned horizontally to the top of the sheet. Now we want to also make sure that we have a sufficient margin here. Since we had 67.5 millimeters along the y-axis, we can do 67.5 here as well. Very good. This would require that the minimum extent of the sheet that you prefer also include a sufficient margin on the far side here. Now we want to subtract the volume of the landscape from the XPS sheet here. And since this landscape consists of one single closed polysurface, it is easy to do. We'll simply select the XPS sheet and do Boolean difference. And then we'll select the polysurface and allow it to calculate. Now, since this Rhino document is a separate file specifically for CAM, we can safely delete this landscape polysurface. And here we see the resultant negative surface that we want to use as our casting formwork. As for the polylines here, it is very, very important to make sure that they do not extend all the way to the edge here. That would mean that when the router bit follows this trace line, it will go past the border of the vertical edge here by half of its diameter or its radius. So let's do like this. Let's make a rectangle that is from one corner to the diagonal corner. And then we can select that with cell last. And now we want to make an offset of this. And the distance of the offset should be the radius of the router bit that we intend to engrave these trace lines with. So in this case we want to use a 12mm flat end mill, thus requiring the offset to be at least 6 millimeters. So the distance should be set to 6. And then we can make the offsets, holding Alt to temporarily disable the snapping. We can delete the original curve, and then entering top view and temporarily hiding our model here with Ctrl H. Now it is very simple to simply select the boundary curve, and then Ctrl T to trim, and I will trim away what is outside of the boundary. Space or enter to confirm, and here we have it. This one we can delete. And then we can Ctrl Alt H to show hidden objects, and we can go back to perspective. And now, with the 3D model prepared, we can select the negative landscape model here with the inset, and then we'll export this. We'll make sure to save it as a Rhino 5 model, and then we can take a previous model as our starting point. We'll adjust the data that need to be adjusted, and then we can export this. Having exported a 3D model as a Rhino 5 3D model file, we can now separately select the polylines and export these separately. We can click the previously exported 3D model file so as to get the file name, and then we'll separately export this as DXF, adding here polylines as a suffix. This should be the 2007 lines export scheme to properly work. Alright, now we can go to Fusion 360. Let's upload the previously exported files. And wait until they have properly been uploaded to Autodesk servers, processed and being ready to open. This might take a while. When the upload process is finished, you can double click to open the 3D model file. And the first thing you can do is to right mouse and click on the polyline document and insert into current design. Then click OK to confirm. Now let's change the workspace from design to manufacture. In here, let's create a new setup. The setup is representative of the physical stock that you put on the workbed. The first thing that you should make sure is that the work origin is placed correctly. At the top of the stock, where the X and Y positive axes are both pointing along the edges of the material, so not where one positive axis points out in the void. So this specific corner. Very good. Go to the second tab, Stock, and make sure the stock side offset is 0. And for this particular workflow, milling a casting formwork, it's important that we have no top offset. Otherwise the CNC will be programmed to also mill all of the top of the sheet here, but we will only cast plaster into this formwork here. So all that milling time would be unnecessary. Given that you have prepared the Rhino model properly, we now have accurate stock dimensions for the physical stock. Again, this is excluding the flanges. Click OK to confirm. Let's save the file with Ctrl S or the floppy disk icon. The version description can be left at user saved. It is not the file name or the document name, but the name of the specific revision that has been saved. Now, when it comes to authoring toolpaths for this model, let's look at the reference data. Go to your preferred web browser and enter cnc.kthcnc.se. It is simply a URL to a Google Drive. In here, you'll find reference photos that might help you in determining what toolpath indices would be interesting to check upon. If we go back to the root and then into the folder Fusion 360, which is the CAM software that we use. In here we have a datasheet of all of the relevant toolpath data for the toolpaths that have been run for the last 7 semesters. So we can hold Ctrl and press the down key to go furthest down. And furthest below here we find a set of references which have been specifically created for this tutorial. So if we hold Shift and scroll to scroll horizontally, we'll see here that the first toolpath is a 3D adaptive one, and it uses the router bit that has been indexed with product ID 23. So we'll go back to Fusion 360 and we'll create a 3D adaptive clearing toolpath. We'll select tool number 23 as our tool. We'll go to the previously imported tool library. We'll go down to 23. And we'll see here that it is of moderate length with a very wide diameter, 16 millimeters. Due to the moderate length, it is important to take note of the length below holder. Here we see that from the bottom of the tool holder's collet down to the tip of the tool, it is 68 millimeters. As such, we'll constrain the said depth of this tool to 67 millimeters, so as not to reach further than it has reach. There are ways around this, but learning how to author your own toolpath, it is better to be safe than sorry. So let's select this, and if we go to the datasheet, let's see the toolpath settings here. As for the spindle speed, we should have the default of 5000 RPM. If one would change the spindle speed, then it is of utmost importance to only change the spindle speed and never the ramp spindle speed, because this parameter, if overwritten, will be erroneously interpreted by the CNC machine, gradually increasing its feed rate instead, running amok and dashing into oblivion. So if you would change the spindle speed, make sure to only change this spindle speed value. It is recommended in Fusion 360 that you only change the digit that you need to change instead of all of the field, due to retaining the unit is equally important. Let's go back to the datasheet. And as for the feed rate, we have in millimeters per minute 4000. So we can change the cutting feed rate from 1000 millimeters per minute to 4000 millimeters per minute. And if we go back to the datasheet, and if we hold Shift and go to the right, the scroll wheel, we see here that we have pull away active. So we'll go back to Fusion 360 and we can activate shaft and holder, and here, making sure that the mode is pull away, will increase the shaft clearance to 2 millimeters, so that is 2 millimeter shaft clearance and 5 millimeter holder clearance. This is a safety measure that makes sure that when generating the toolpath, should the smooth shank, which has no sharp flutes as its flute length, collide with unmilled material, then it would not allow so, but instead pull away. As for the second tab, Geometry, we can see here in the reference that we need no machining boundary, and we should have rest machining active. Rest machining means remaining stock machining, and it means that succeeding toolpaths will take into account what previous toolpaths have actually removed, so that succeeding toolpaths are not milling the same volume twice. In the third tab, we'll have to make sure that the bottom height is restricted so as not to go from the stock top no further than -67 millimeters, 1 millimeter less than the range of the tool from tip to collet. In the fourth tab, passes, we may check the reference, where it says here that the direction should be climb milling. Climb milling reduces the amount of rubbing between the sharp flutes and the material, and in plastics such as extruded polystyrene, it is important to do so. As for the maximum roughing step down, we have found that 20 millimeters is the reasonable maximum without too much of plastic chips being produced. As for the fine step down, the increments between the maximum roughing step downs, we can check the datasheet. We have 10 millimeters as fine step down. So we'll change this to 10. For this toolpath, let's disable flat area detection. It adds an awful amount of computation time and is not practically relevant for our purposes. As for the stock to leave, since this wide diameter tool will excessively chip or rip the plastics, we'll make sure to leave a radial and axial stock to leave of 4 millimeters. We don't need to change any settings in the linking for this specific tool, so we can go back to passes, make sure that everything is correct, and click OK to generate the toolpath. Fusion 360 often jumps to the back, so to say, so let's Alt-Tab back. Looking here at the lower right of the user interface, we see that we have a simulated machining time of 22 minutes. The actual time it takes to mill will never be the same as a simulated time, and depending on the type of toolpath, different deviations of actual milling time are statistically usual. For singular toolpaths, it might be easier to simply multiply 22 times 1.8 and get the maximum reasonable actual time to mill. Since we are authoring several toolpaths of different types, we can go to Rhino and we can open Grasshopper and expand the window, and then we can open this definition to estimate CNC toolpath times. If you go to your preferred web browser and you go to gh as in grasshopper.kthcnc.se, it's simply a URL to a Google Drive. Then you may go to definitions, fabrication, and estimate CNC toolpath times, where you have the definition itself as well as an image preview of it. If we go back to Grasshopper, then we can add here 22 minutes for our first toolpath. It is a 3D adaptive one. And that takes 40 minutes, and 40 minutes are well below the maximum total of 6 hours, but we have several toolpaths left to author. The next toolpath is a little special. It's an intermediary one in nature, and only relevant when you have these vertical walls that extends very far. Or instead of being unspecific as in very far, if any vertical wall extends further than the flute length of any tool that is used for a parallel toolpath, then we must use an intermediary 3D adaptive clearing toolpath with the same tool. If we go back to the datasheet and highlight the next row here, we see that it is a 3D adaptive toolpath using tool product ID 19. So let's do so. A 3D adaptive clearing toolpath, and let's change the tool. And let's go to the previously imported tool library, and let's go down to number 19. Here we see that the tool is very long. It has a flute length of 61 millimeters, which is very generous and might actually suffice to reach the deepest part of the negative model. But engaging with 61 millimeters of material is a lot, and a 3D parallel toolpath will not take into account how much material it laterally engages with. So it is wise to prepare for the succeeding parallel toolpath with a 3D adaptive clearing toolpath with the same tool, but only milling the final surfaces of the upper parts of the model, while allowing the lower part of the model to be defined by the succeeding parallel toolpath. Since the previous toolpath had a maximum roughing step down of 20 millimeters, about 1/3 of this, then we should perhaps allow that the succeeding toolpath engages in maximum 30 to 40 millimeters of material, but not the full 61. XPS is a fairly soft material, so this is not as critical a matter as it would have been if milling in wood. Let's select this tool. As for the spindle speed and cutting feed rate, let's check the datasheets. We have a suggestion of 10,000 RPM as spindle speed. And as for the cutting feed rate, 2,500 millimeters per minute. We should enable shaft and holder, making sure that the mode is pull away, and increase the shaft clearance to 2 millimeters. If we go to the second tab here, we have a machining boundary set to none, and we have rest machining with the source being the result of the previous operation. If we go to the third tab, heights, this specific tool If we go here to manage and tool library here and just click here to select it, the length below tool holder 125 millimeters exceeds the thickness of the material on the workbed. As such, the reach of this tool totally accommodates this 3D model, so we don't need to restrain the bottom height. In the fourth tab, passes, let's make sure that it is climb milling, and then the maximum roughing step down, it might be set to 10 millimeters, and the fine step down, it might be set to 5 millimeters. Let's see here if this is corroborated by the reference. If we scroll to the right here we see that we have a maximum pass depth of 20 millimeters suggested, as well as a fine step down of 10 millimeters. While perhaps the reference settings are not too aggressive, in this scenario we prefer to set a maximum roughing step down of half, since the maximum roughing step downs, they define the larger increments that the tool descends in a material, and if we have a large roughing step down with a larger major increment, then we might not be allowing the toolpath to go as deep as we intended to go. Flat tire detection should be disabled. Here it is very important with the stock to leave. If we would disable the stock to leave, that means that the toolpath would be generated as if the final result of the model should be achieved. We do not want that. We want to have 0 millimeter of radial stock to leave. We don't want the toolpath to leave any residual margin that might be obstructing for the succeeding parallel toolpath. But as for the axial stock to leave, we can increase this to perhaps, I think in the reference it was set to 36. And this value defines what the succeeding toolpath will have left as its maximum axial or vertical margin to the final model. Setting this too high will result in an excessive engagement of the succeeding parallel toolpath, and setting this too low will simply mean that we use an awful amount of time for this toolpath, and then the engagement of the succeeding toolpath that actually defines the final surface becomes very minor. So we can do 36 millimeters here. When setting this value, it is very important to also note that if the axial stock to leave is larger than the clearance height or the retraction height, then Fusion 360 will lift up the clearance height to a Z position that is 36 millimeters in this case above the top of the surface as well. This is actually impossible for our circumstances. The CNC machine will freeze because we have 100 millimeter of material thickness, we have 125 millimeter of tool reach, so to say, length from bottom of tool holder to tip of the tool. So the axial stock to leave would have to be set so as to accommodate the clearance height and the retraction height itself. And we see that the clearance height is 10 millimeters positive from the retraction height, and the retraction height is 5 millimeters above the stock top. So we'll need to reduce this to no more than 15, let's do 14. In the linking tab, we don't need to change anything. We can click OK and Alt tab back. And we see here that we did get a warning that the retraction height has been lifted to a safe height. And that is expected. Our axial stock to leave was within the clearance height, but not within the retraction height. So the retraction height has been lifted to a safe height. As long as we set the axial stock to leave to a suitable mount, it is no problem at all. If we simulate this toolpath and go to the end of the toolpath, we see here that it takes away material from the edges where the succeeding toolpath would have difficulty defining due to the depth of the model. Very good. We can exit simulation. If we go back to the datasheet, we see here that the next one is a 3D parallel one. Let's highlight this row. A 3D parallel toolpath with the very same tool. Let's create a 3D parallel toolpath. And by default, the same tool of the previous toolpath is set here as default. So that's perfect. If we want to verify this, we can click select. And here we see that we have product ID 19. If we would click select, then the default spindle speed and cutting feed rate of this tool will be overwriting the ones that were previously set here. So let's click cancel. And here we see that we still have a spindle speed of 10,000 and a cutting feed rate of 2,500. If we go to the datasheet and hold shift and scroll to see here, this is correct. We see here that we have pull away active with 2mm shaft and 5mm holder clearance. So let's go back to Fusion 360 and enable shaft and holder. Make sure that the mode is set to pull away and increase the shaft clearance to 2mm. In the second tab here, the geometry tab here, so as to make sure that the toolpath is not going all over the top of the surface here, let's make sure to change the machining boundary to selection. And then let's select this specific boundary. The tool should be contained inside the boundary with no additional offset. If we go back to the datasheet, we see here that we don't need to have any rest machining active. we can leave it at the default disable state. That is because the 3D parallel toolpath is distinct to the 3D adaptive clearing toolpath, and they have different logics in how they approach the surface, so we don't need it active for this one. If we go to the third tab, heights, we don't need to change anything because the range of the tool is sufficient, and the previous intermediary 3D adaptive clearing tool also has diminished the lateral material left for the upper segments of the model relative to the lowermost surface. If we go to the fourth tab, passes, while generally recommended to only go one way or climb milling in plastic, we have found that for a 3D parallel toolpath with a moderate step over and when the depth of the vertical walls have been diminished, it is not a problem to go both ways, thus reducing the time it takes to mill. Let's see, as for the step over, the increments along the perpendicular axis to the one that it traverses parallel to. Let's look at the datasheet. We have a step over of 3 millimeters. 30% of the diameter of the tool. And then the reference also suggested that we should add the perpendicular pass. That means that first going along the x-axis with 0° pass direction, and then defining the model once again, but perpendicularly along the y-axis. In a material with a grain direction, it is always suggested to go simply along the grain with no added perpendicular pass. But in XPS, which has no grain direction, it might actually be more beneficial within the same time to have a relatively large step over and going both along the x and y axes than halving the step over and having no perpendicular pass. Since the material has no grain direction, it does not influence the final surface texture, whether going one way or the other. We don't need to change anything for the multi-axis tab or the 6th tab linking. We can go back to passes, make sure that everything looks correctly here. As an initial test, we will not have a perpendicular pass added. A parallel toolpath is, opposed to the 3D adaptive one, very linear in nature, so it's very easy to estimate the increase or decrease in time when increasing or decreasing the step over or when adding a perpendicular pass or not. So let's click OK to generate. Now we see here two things. One, with no perpendicular pass added, it is only along two in the edges that the vertical wall is within tolerance properly defined, while the relatively high step over does not allow for the other two walls to be properly defined, while the relatively high step over will not line up with this wall here. Adding a perpendicular pass will solve this. The simulated time is only 34 minutes. We can add the second and the third to the Grasshopper definition for estimating toolpath times. So here we have 3 minutes of 3D adaptive. So let's add 3 minutes of 3D adaptive for the second one. Takes up to 6 minutes as a reasonable max time for the toolpath. And then the third one was a 3D parallel going both ways, and it took 34 minutes. So let's change this to 34. And then let's see here, for these 3 toolpaths, the whole operation will most reasonably be done within 1.5 hours. If we also go back here and check the simulated result and go to the end of the toolpath and temporarily hide all the models, we see that this is fairly rough in several ways. So with these circumstances, if we would add a perpendicular pass, that means that we have a time factor of 2, since we simply have twice the distance to cover. And then if we also reduce the step over from 3 millimeters to 1.5, that would of course multiply the time factor by a factor of 2, and that means that the total amount is predicted to take 4 times longer. So 4 times 36 minutes is 144, subtracted with 120, that's 2 hours and 24 minutes. So 2 hours and 24 minutes. And then we'll see here that we have an estimated reasonable maximum time of 3.5 hours. While being able to push this further, let's see what results we actually are simulated to get. It might be totally sufficient. So let's go back to Fusion 360, exit simulation, and let's change the settings here. So double clicking the icon here and going to passes, adding a perpendicular pass and reducing the step over from 3 to 1.5. Let's click OK to generate. Alright, so now we see here a much more densely populated grid of lines here, so we'll go to actions and simulate, and then we can do the same as previously. We can simply go to the end of the toolpath, and now we see here already with the reduced step over, we see only going along the x-axis yields a much better surface, and then going along the perpendicular y-axis, it even more so improves. Very good. One has to take into account that the size of the model will of course affect how long it takes to mill, and the adding or not of the perpendicular pass and the adjustment of step over is something to be done within reason to the time it takes to mill. We can exit the simulation, and then checking the datasheet, The next toolpath is a 2D trace operation with product ID number 1. So we can highlight this row and then we'll go back to Fusion 360. We'll add a 2D trace operation. We can also show the models again, and then we'll choose another tool and we'll go to the previously imported tool library and we'll select product ID number 1 here. It is a 12mm in diameter flat end mill. The length below the holder is also more than sufficient for reaching all of the model. Let's click select. And as for the spindle speed and cutting feed rate, let's check the datasheet. We have a suggestion of 9,000 RPM, 9,000 RPM. And as for the cutting feed rate, we have a suggestion of 2,000 millimeters per minute. And the 2D trace operation will simply follow the trace curve, so there are no more refined 3D functionalities such as pull away. Let's go to the second tab, and then selecting the curves here, we should expand the models, we should expand this specific document, we should expand the reference document, we should expand the sketches subfolder, and then we may select the roads layer here. And then in the third tab, heights, there is nothing to be changed. And then in the fourth tab, passes, we'll make sure that the sideways compensation is centered. And then the axial offset here is how deep the tool should descend into the material here, relative to the said height of the curve. So we'll do -1 here. In the linking tab, we should not change anything. So let's go back to passes, make sure everything is correct, and then click OK. If we go to actions and simulate, and make sure to hide the models. And if we go to the end of the toolpath, we see here that with a descended groove in the negative model, this will actually yield an elevated marking of rectangular profile along the trace line. As these elevated building footprints will be descended, this descended representation of roads will be elevated. We also see here that we have properly trimmed the polylines so as not to extend further close than the radius of the router bits. There should be no significant collision between this toolpath and previously unmilled material. However, one sees here that it might be prudent to increase the offset of 1 mm more, since we evidently have some small touching here. We can exit simulation, and then we'll add another 2D trace operation. Let's highlight the last one here. It's a 2D trace operation, and here the tool is set to the product ID 27. We will preface this that this is a very, very short tool and might not at all be suitable for this operation. Let's see. If we add a 2D trace operation, and let's make sure that we use tool product ID number 27, and you see that this is very, very short. It only has a 25 mm range from the tip of the tool to the bottom of the tool holder. Let's select it anyway. We will most probably need to change this. And the suggested settings for spindle speed and cutting feed rates are 12,000 and 2,000. So 12,000 RPM as spindle speed and 2,000 millimeters per minute as cutting feed rates. If we go to the second tab, geometry, then we should select the property line here. If we also show all of the models, we see here that this is going to get really deep there, as well as here, there. This might be totally unsuitable, and we'll most probably have to change the tool to one with a longer reach. As for the heights, we don't need to change anything. In the fourth tab, passes, let's make sure that we disable chamfer, and the axial offset, we can set it here to -0.3 initially. A very, very subtle engraving. Again, as with the previous one, since we're doing a descended groove, this will actually be, when casted, an elevated marking. So be aware of that. In the linking tab, we don't need to change anything. We can go back to passes, make sure everything is correct, and click OK. Now, when we simulate this, we immediately get a collision between the stock and the tool holder. If we go to the second tab, info, there is only one collision registered actually. Let us, with a moderate playback speed, play this. And there you see, it is quite dramatic, and although it showed here as simply being able to progress, in reality this would be a most critical collision, and there can be no good outcome of this. The worst might be that the Z-axis of the CNC machine might break. So that is of course 100% not acceptable. Just being curious about this, let's see how it handles when it progresses here. It should be a collision there as well. No, here it actually managed. The depth there was insufficient, while the depth here was actually accommodating the reach of this tool. If we go back slightly, we can see this more clearly. So this makes it really important to actually visually verify these 2D trace operations, since the 2D operations don't have any refined pull away functionality as a safety measure. So let's exit here, and then we'll positively have to change the tool here. So we'll change it to something that has a longer reach, a larger length below holder than 25 significantly. And while the tool library in Fusion 360 holds all of the data, it might be easier to simply go to cnc.ktacnc.se. It's simply a URL to a Google Drive, to go to Fusion 360, to go to tool library, and then to open this datasheet with the same tools. Then we can highlight the length below collet, while also searching for something of a sufficiently small cutting diameter. We see that number 4 here has an equally restricted length below collet and will produce the same collision between unmilled stock and the tool holder. This one looks promising. Although it is a ball end mill, and ball end mill generally yields inferior surfaces when milling in XPS, perhaps due to the extruded nature of the extruded polystyrene, it might still be a good idea to use this thanks to its moderate reach and very small cutting diameter. Let's choose tool number 9. Let's go back to Fusion 360. And tool number 9 is here, and here we see a representation of it. It has a wider shaft than its flute diameter, so take that into account. Let's select it. And then as for the spindle speed and cutting feed rate of this, let's go to the datasheet and go back to the community feeds and speeds. And then we can do as simple as this. We can Control F to search, and then we can search for tool number 9. And then we can go to the relevant column here, and then we can see where we last milled in XPS with tool number 9. So we go to 9, and we have 9 here. It was in a chipboard with inferior results. Here we milled with number 9 in birchwood. Here we milled with number 9 in birchwood as well, and here we milled with number 9 in XPS. So highlighting this field, we can see here that we have a spindle speed of 11,000 and a cutting feed rate of 1,750. So let us input these as our speeds and feeds. So we have spindle speed 11,000 and cutting feed rate 1,750. The rest of the settings might not need to be changed, but perhaps it is beneficial to change the axial offsets now that we don't have a V groove and instead a 4mm ball end mill. We might want to have an axial offset of -2 mm. We'll see how it looks in the simulated results. Let's click OK to generate, and then we can go to Actions and Simulate. And here we see that we have a significantly longer reach. We can temporarily hide the models, and then we can push play. Not a problem at all. Very good. We might want to reduce the axial offset from -2 mm to -1. Very good. And we can exit simulation, and then we can double click, and then we can go to passes, and we'll reduce the axial offset to -1. Click OK to confirm, and let's simulate once again. Here we can actually just go to end of the toolpath. While not being 100% certain of the significance of the change, we see that this might be an acceptable result. We can exit the simulation. Now, with these 5 toolpaths properly defined, let us first very briefly add the simulated time of these 2 2D trace operations. They are less than 1 minute each. They can be rounded to 1 minute each. So we'll add for the 4th one 1 minute of 2D operation, and for the 5th one 1 minute of 2D operation. Now we have a total of 3 hours and 33 minutes. While we still would have time left within the maximum total of 6 hours, if we get a perfectly fine result in less of a time, then that is perfectly suitable. Let's go back to Fusion 360, and now, having properly authored all 5 of these toolpaths, we should verify that none of them have any critical collisions registered. So let's begin with the first one, go to Actions and Simulate, and here in the second tab, Info, we see the progression of the collision registration, and we see that we have no collision registered. Very good. We can exit simulation. We can click the second one and simulate. And we'll go to the second tab where we see that there are no collisions registered here either. Very good. We'll go to the third one and we'll go to Actions and Simulate. In the Info tab, we'll wait for the progression of the collision registration. As for this third toolpath, we have no registered collisions as well. Let's click Exit Simulation. And these 2D trace operations are important to visually verify. They usually don't take too long to visually verify, but as you saw previously with the 5th one, it is of utmost importance to see the effect of any collisions. So let's click play to start a playback. And that was no problem at all. we can increase the playback speed slightly. Let's see here, that works very well as well. It touches upon the surface there, but that is not by a significant amount. Very good, no critical collisions. Click X simulation and simulate the fifth and final one and push play. We previously did this. Very good, no collisions at all. Click X simulation. Now, when all these 5 toolpaths have been verified to be reasonable to mill with regards to time, and also verified to be free of any critical collisions, that is, safe to run, we are ready to post-process these. So let's select the first one. While it is possible to post-process all of the toolpaths at once as a combined toolpath, it is recommended to export them individually, due to the simple fact that not too regularly, but perhaps once every 2 or 3 weeks, the CNC machine freezes during operation. And during such a freeze-up, one would have to either restart the toolpath or manually split it. And for those scenarios, it makes it much more easier if the toolpaths are post-processed individually. So let's do so. Let's select the first one, go to Actions, Post-Process, and here, make sure to select the post-processor that is relevant for the machine that you're going to use. Select it from your previously imported post-processor library, and make positively sure not to click these icons to update the post-process to the latest available version. Updating would mean overwriting our custom changes to these post-processors so as to make them work for our machines, and as such make positively sure not to update. When you have selected the post-processor that is relevant to your use, click Select, and then make sure that the output folder that you may specify is one that you can clearly find the contents of. The naming of the post-processed and exported toolpath files are very strict in formatting or syntax. That is due to the fact that the CNC machine will not accept any file that has any special characters, any points, any spaces, any other punctuation symbols, and it also has a very constrained graphics user interface, showing only the first 1.5 dozen or so of the characters. As such, please name your toolpath files as this. The date of your scheduled CNC milling in a big endian format, such as this, 24/06/15. Underscore the order of the toolpath, in this case the first one, so 1. Underscore what tool holder is used for the toolpath's tool, in this case tool holder 1. Then you may suffix the file name by anything you like. Just make sure that you exclude special characters, white space, and punctuation symbols. So this can be Norrbyskogen underscore XPS underscore building footprints underscore smooth underscore casting formwork. But it might also be left as this. Before posting, effectively exporting the file, make sure to select everything in the name field here with Ctrl A and Ctrl C to copy it. That makes it much easier to repeat the process for the other toolpaths. Click Post. Now you see that the toolpath has been successfully posted, and you may go on to the next one. So let's select it, go to Actions and Post Process, simply Ctrl V and paste this. Let's change the order from 1 to 2. This is the second toolpath, and the tool holder that is used is tool holder number 2. And you can post, and it was successfully posted, very good. Then we'll move on to the third, and we click Actions and Post Process, Ctrl V to paste. This is the third toolpath, and the tool holder that is used is tool holder number 2, the same as the second one. We can click Post, successfully posted, very good. We'll move on to the fourth, and go to Actions and Post Process, Ctrl V to paste, and this is the fourth toolpath. It uses the tool holder 5, and we can post this. Successfully posted, very good. And we'll go to the fifth and final one, and Actions and Post Process, and Ctrl V to paste, and I will change the order to 5 and the tool holder to 4. Very good. We can now post this, and it has been successfully posted. Very good. While you now are finished with the workflow of preparing toolpaths for this specific model, one thing that makes it very easy to download these toolpath files for your scheduled milling is to go to your preferred web browser, enter cnc.kthcnc.se. It's simply a URL to a Google Drive. and go to it. In here, there is one folder called temporary storage. If you enter this and create a new folder with your name or anything significant for this scenario, and in this folder, you may simply click and drag the toolpaths that you post-processed and exported into this folder. That will make it really easy to, on the date of your scheduled milling, download these files on the computer that is connected to the CNC machine and send them to it. One added bonus is that if you want to get an accurate visual representation of the simulated stock after milling, is that you can select the whole of the setup, go to Actions and Simulate, temporarily hide the models, and then simply go to the end of the toolpath. This will, with a much higher visual fidelity for the whole process, generate a simulated mesh for the operation. And while Fusion 360 is a very competent program, it might be easier to visualize this stock in Rhino. So right mouse and click on the stock, go to Stock and Save Stock, save the stock in any directory that you easily find, and click Save. And then you can go to your Rhino file, and we can minimize this. And then we can simply go to the folder where we exported it and click and drag it into the Rhino window and make sure to import it. And default STL import settings work fine. We can move this in the positive y-axis of perhaps 600 millimeters, and then we can change the display mode from shaded to Arctic. And now we see a more accurate representation of how the milled model will look like. This is of course the negative formwork, so one has to take into account that the final model will of course be the inverted positive of this. Having successfully authored your toolpaths and uploaded them to the temporary storage folder, you may now shift your focus into preparing the physical stock for the CNC milling. In this specific scenario of milling a negative casting formwork in XPS, it is very simple. While the representation of the XPS sheet is without the flanges, the XPS sheet might actually be simply put on the workbed as is, as long as the work origin is properly set, that is, excluding the flanges. Thank you for your time.